Another episode of PaperCast, the podcast where we break down the latest and most exciting research in machine learning. I am Justin, your senior researcher host, and with me is Emma, our brilliant PhD student co-host. Today, we have an incredibly fascinating paper to discuss, one that blends nostalgia with cutting-edge AI. That's just titled Diffusion Models Are Real-Time Game Engines by Dani, Valevski, Yaniv, Leviathan, Moab, and Shlomi, Fruchter, a team from Google Research Today. Emma?
Absolutely. Justin, what immediately caught my attention is that the authors have managed to get a neural network to simulate the classic game Doom in real time. This isn't just running Doom on a smart fridge. This is about using a diffusion model to create the game size environment dynamically frame by frame as you play. It's made intuitive and around Doom taken to a whole new level.
Exactly. The main contribution of this paper is Game Engine, a real-time game engine powered entirely by a neural model. The core innovation here is using a generative diffusion model to produce the next game frame based on the sequence of past frames and player actions. This approach is different from traditional game engines that rely on manually written code to update games and render frames. So, Endo, can you explain how Game Engine fits into the broader AI landscape?
Sure thing. Game Engine represents a significant shift in how we think about interactive simulations. Traditionally, game engines like Unreal or Unity rely heavily on handcrafted rules and optimizations to simulate complex environments. Game Engine, on the other hand, leverages neural networks to learn these rules and generate high-quality frames in real time. This approach could potentially simplify game development and open up new possibilities for interactive reactor with the printer.
That's a great analogy. Emma, one key innovation in GameEn is its ability to maintain visual quality while generating frames at 20 frames per second on a single computer. To put this into perspective, think of a diffusion model as a highly skilled painter who can quickly sketch the next scene in a movie based on the previous scenes. And the director's cues, the challenge is to keep the sketches consistent and high quality, even as the director just keeps changing the script on the fly.
Right. And the authors achieved this by training their model in two phases. First, they used a reinforcement learning RL agent to play the game and record the training sessions. Then they trained a diffusion model to generate the next frame based on the sequence of past frames and actions. This two-phase training ensures that the model can handle long trajectories and complex game state updates, like tagging health and hemo, like attacking enemies and so on.
Speaking of real-world impact, imagine the potential applications outside of gaming. For instance, this technology could revolutionize virtual reality VR and augmented reality art experiences by providing more realistic and responsive environments. It could also be used in training simulations where real-time feedback and high visual fidelity are really crucial.
Definitely. However, it's important to address some limitations. One major drawback identified in the paper is the model's limited memory. It can only access a little over 3 seconds of history, which can lead to inaccuracies in maintaining long-term game states. Additionally, the behavior of the RL agent doesn't like to perfectly mimic human players, which can result in less realistic simulations in certain scenarios.
Good point, Emma. There's also the hardware consideration. While TPOs are powerful, they are not as widely accessible as consumer GPUs. Maybe this could limit the immediate adoption of Game Engine in mainstream gaming or other applications. Plus, the Model S performance could degrade if we try to run it on less powerful hardware.
Right? And looking ahead, there are several exciting research directions, for example, extending this approach to other types of interactive software beyond games could be groundbreaking. Also improving the Model S memory capacity and making it more hardware efficient would be crucial steps forward. Another interesting avenue is enhancing the agent's training to better mimic human gameplay, perhaps by incorporating more sophisticated RL techniques or human just-in-the-loop training.
Absolutely. And this research could also draw from or impact other fields like computer graphics, robotics, and even cognitive science. The idea of using neural models to simulate complex environments has far-reaching implications, and it will be really fascinating to see how this evolves.
Just a thought-provoking question for our audience. How do you think the integration of neural models in game engines will change the future of game development and interactive media?
That is a great question to ponder. Until next time, keep exploring the frontiers of AI. Good luck, infinity and beyond.